are just 34 minutes away from launching this Atlas V rocket you see right there on your screen. On board are several payloads, including NASA technology that could revolutionize how we communicate to and from space. Thank you for joining me for today's live launch coverage of NASA's Laser Communications Relay Demonstration, or LCRD. I'm Megan Cruz, and I'm joining you live from NASA's Kennedy Space Center in Florida. Today's 2-hour launch window opens at 4:04 a.m. Eastern Time, and that rocket you just saw sitting on Space Launch Complex 41 at Cape Canaveral Space Force Station, which is just behind me across the water here. Now, LCRD is hitching a ride on the U.S. Space Force's Space Test Program 3 mission, or STP-3. You can think of the Space Test Program as a ride share to space. It's primarily for the Department of Defense to send up science and technology experiments, but if there's room, others can share that ride, and that's what NASA is doing today. So what does LCRD look like? Well, there it is in the middle of your screen there, about as big as a king-size mattress, sharing a spacecraft with other payloads. It will showcase the unique benefits of laser, also known as optical communications. NASA has relied on radio communications since we first started exploring space, but as we fly more missions that generate more data, and as we work to establish a presence on the moon and send humans to Mars, we are of course going to need a communications upgrade. Lasers can transfer a lot more data at once. How much more? We'll say there's a high-resolution map of Mars. It would take about 9 weeks, yes, 9 weeks, to send that map to Earth using radio waves. But using lasers would only take 9 days. Now, coming up, I'll introduce you to 2 people who played critical roles in bringing LCRD to life. But first, let's check in with our friends at United Launch Alliance. We have Andrea Lenhoff here with me this morning. Andrea, how's the rocket looking?
Thanks, Megan. Everything is going well here in the ASOC. The Atlas V is fueled and ready to launch STP-3 in just about 30 minutes. The launch count is about to enter a 30-minute hold. This planned hold gives our team extra time to address any last-minute issues. At this time, the team is not working any issues, and we are proceeding towards an on-time liftoff at 4:04 a.m. Eastern. The Space Launch Delta 45 weather officer will provide a final brief to the team shortly. As you know, though, Megan, the weather's been beautiful here, and we're not expecting that to change during our 2-hour launch window today. Back to you.
All right, thanks so much, Andrea. Now, we are about 30 minutes and counting, about 6.5 hours from liftoff today. We will see LCRD's host spacecraft separate from the payload fairing. It will make its way to an orbit of around 22,000 miles above the Earth's surface. That's about 1/10 of the way to the moon, for those wondering. By early January, researchers will begin powering on LCRD, and by March, they hope to begin conducting the first experiments. You can see a graphic right there, an animated graphic of LCRD. Again, that's what it's going to look like once we launch it and we start conducting experiments in March. Now, researchers will spend the next 2 years testing LCRD by beaming invisible near-infrared lasers to and from 2 ground stations on Earth, one in California and one in Hawaii. These remote, high-altitude locations were chosen for their clear weather conditions, as clouds can disrupt laser signals. You can see some of the ground stations there. If all goes as planned, LCRD will be NASA's first 2-way, end-to-end optical relay because it can both send and receive data at once. And now I'd like to bring in Kathy Leaders, Associate Administrator of NASA's Space Operations Mission Directorate. Thank you for carving out the time to be here with me.
Thank you for having me.
Perfect.
Very, very exciting day.
Yeah, absolutely. Tell me a little bit about the directorate and your role there.
So I get to be lucky enough to be in charge of space operations, which means we get to work on the operational missions that are in play today, but also getting ready for exploration missions. And this one's a very important one to get us ready to go back to the moon.
Yeah, so tell me, what are we hoping to learn with LCRD today?
Well, we actually need to improve our comm systems to be able to do human spaceflight activities around the moon. And so this demonstration is very, very important to get our new systems going. I was just talking to Badra Yunus in charge of our scan group, and he said, you know, this demonstration, if it doesn't work, could push us back 5 to 10 years. So this is very, very, very critical for us to be able to prove out the systems that we're going to need to get ready for both Artemis 2, Artemis 3 are very, very complicated missions, and getting ready even to be able to prove the systems that we'll need to go to Mars.
Right. And it is so critical that LCRD isn't the only mission, right, that's studying laser communications?
Absolutely. On Artemis 2, we actually have O2O, which is a critical system for us to be able to prove out, can we do comm between the relays and the Artemis 2 spacecraft, the Orion spacecraft that will be carrying our first crew demonstration mission. And then we've got Illumina that's going up to the space station that will be doing our space-to-space comm between LCRD and the International Space Station. And then next summer we have Psyche that's going up that will be taking our deep space comm unit, so we'll be practicing it in our deep space area. So
wow.
It is going to be like an exciting next year of comm and checking the system out, but we need to get the system checked out before we do our moon missions.
Right. And laser communications wouldn't completely go in place of radio, right? This would supplement our radio communications?
Absolutely, but it's going to be a workhorse for us. When you see what we need to be able to have comm for human systems, it's a big deal.
Right.
One of my favorite analogies of how this system improved, you talked about a few things, but you know, for those of us that have been working at home during COVID, this is the difference between dial-up comm and, you know, high-speed internet. So
right.
I know when my internet starts going down, I'm in big trouble in my workplace. So this is going to be an important system for us.
Yeah, well, we don't want NASA's internet to go down, right?
No, we do not want NASA's, not its moon internet.
Right. Kathy, thank you so much. I really appreciate you being here today.
Thank you.
All right, so getting more data back faster is, of course, a plus, but there are other benefits to laser communications, so check out this video to explain.
Since 1958, NASA has relied on radio wave technology to talk with missions in space. Today, we're developing a better way to get spacecraft data back to Earth. That's where the Laser Communications Relay Demonstration, or LCRD, comes in. Built and managed by NASA's Goddard Space Flight Center, LCRD will send and receive near-infrared laser beams to and from Earth. As NASA's first long-duration test of optical communications technology, the mission aims to perfect space and ground-based technologies. So why lasers? Laser communications can transmit up to 100 times more data per second than previous systems by using a shorter wavelength of energy. With this increased bandwidth, missions can send larger files and even live high-definition video from space. Laser communication systems are smaller and more efficient than radio wave technology. They leave more room for science instruments, are cheaper to launch, and require less energy on board the spacecraft. These benefits extend to receivers on the ground. Earth-based laser communication receivers can be up to 44 times smaller than the current radio antennas. LCRD is the next step in making these technologies a reality, helping NASA to push the boundaries of scientific discovery and exploration. Eventually, NASA will integrate this technology into future missions, as well as share it with commercial companies.
All right, we're now about 25 minutes away from launch. Joining me now is Glenn Jackson. He's the one leading the LCRD team. How are you, Glenn?
Very excited.
It's very hard when you have two first names, you know what I mean? So how long have you been working on
7
LCRD?
years, Megan.
Wow,
Yeah, it's been a long time in the making.
Yeah. And thank you so much for bringing these models. I think this will really help to demonstrate to our viewers what LCRD is. So can you walk me through this?
Oh, certainly. So on the left here, I have the whole Sat-6 spacecraft. LCRD is this part of the spacecraft.
Right.
It's about the size of a king-size bed. It has 2 optical modules. They're basically telescopes that look down to the Earth and look at our 2 ground stations in Hawaii and California.
Okay.
So this is 10th scale, but this is a full-scale optical module. This is the telescope that will do bidirectional communications. So the lasers come into this telescope and will be going to the Earth and coming back. Right now it's in the launch latch position.
Okay.
So over on the rocket right now, it is launched, ready to fly. Once we fly and reach geo orbit, that latch will release. We will slew over, and there's the telescope. The telescopes can now look at California or Hawaii. Also later on in the mission, we'll be looking at Illumina-T on the International Space Station. So we can slew left and right,
Right.
and up and down, and track the space station.
And again, this is a full-size model of what we see here, right?
That is correct.
Okay.
Yep, this is full scale.
And this is where the lasers will actually come to in and out of, right?
Exactly. It's bidirectional, and by that I mean we can communicate with the lasers in and out of the same telescope through the Earth's atmosphere. This is very unique for LCRD.
Right. And again, the lasers are invisible, but we're
They
talking
are.
about the diameter of what we see here.
Yes, this is 10-centimeter diameter, and this will be going 22,000 miles through the Earth's atmosphere to JPL's Octolab and to Hawaii.
And do you think this could be a game changer for how we do business here
This
at
is
NASA?
definitely a game changer. So it's a game changer for exploration in science. Optical comm has the potential to reduce the weight of communication systems, decrease the power use, and we get 10 to 100 times the bandwidth capability. That's a huge game changer for those people planning missions and getting ready for a presence at the moon and exploring Mars.
Wow. How hard was it to come up with something like this? Again, to move us from radio communications to hopefully laser communications.
It is a lot of hard work. We have an amazing team, great partnership with Lincoln Laboratory and a technology transfer activity. The team has been working for about a decade on this. We're very excited tonight to start the mission.
Oh, perfect. And you know, Kathy alluded to think of this as kind of like our internet at home. But I do want to know, will this technology benefit us here on Earth, sitting at home?
That's a good question. So over the next 2 years, we're going to do experiments. When we do those experiments, we're going to try different operational techniques. We're going to operate through the atmosphere. We're also going to do pointing acquisition and tracking. So basically pointing a laser beam through the atmosphere over 22,000 kilometers,
Wow.
22,000 miles. All of that data will inform future NASA and commercial missions coming up for optical communication. Now, greater communication bandwidth benefits business and the public.
Yeah, absolutely. No, I'm so excited for you. Again, you've been working on this for 7 years. You know, I'm sure this is a labor of love coming to
Yes.
fruition today. So I know you'll have your eyes to the sky as LCRD launches today.
Thank you much.
Thank you so much, Glenn. All right, so after the experimental phase, you kind of heard Glenn talk about it, LCRD will begin supporting in-space missions. In 2023, there will be a laser communications terminal on the International Space Station called Illuma-T. Illuma-T will collect data, from science experiments aboard the orbiting laboratory and then transmit that data to LCRD, which will then send that data to one of the 2 ground stations we talked about for research on Earth to begin studying. And now, with only about 20 minutes left to launch, we are going to kick it over to ULA to take us through liftoff and ascent of the STP-3 mission carrying NASA's Laser Communications Relay Demonstration.
Launch director.
Launch vehicle is ready for launch.
We have ignition.
You have permission to launch.
1 and liftoff. Liftoff of the United Launch Alliance Atlas V rocket.
Mach 1, execute, and we have an indication of spacecraft separation.
Good morning, I'm Andrea Linhoff. I'm a systems engineering lead at ULA and your host for today's Atlas V STP-3 launch for the United States Space Force. I'm here in Mission Control at the Atlas Spaceflight Operations Center at Cape Canaveral Space Force Station in Florida. Welcome to our NASA viewers and those of you just now tuning in. Liftoff is scheduled for 4:04 a.m. Eastern Time, though we do have a 2-hour launch window available today. In addition to watching our webcast, you can also follow live mission progress at ulalaunch.com. The countdown is currently in a 30-minute planned hold. We have 2 planned hold in our 7.5-hour launch count, which give our team additional time to resolve any issues prior to entering the terminal count. At this time, the team is not working any issues and we are proceeding towards an on-time liftoff. Stay tuned after liftoff when I'll be joined by Ruag Zemakotes to discuss the first flight of a new payload fairing in Northrop Grumman's STP-SAT-6 Program Director Ray Crow. The ascent to orbit is more than 7 hours, so we'll wrap up about 15 minutes after liftoff, sending it back to NASA's LCRD coverage. The launch team recently received a final weather briefing. Here's Space Launch Delta 45 Weather Officer Brian Cizik to give us the forecast.
Thanks, Andrea. And the weather is certainly setting the stage for a beautiful early morning launch here from Cape Canaveral. And that's all thanks to the fact that we're really in between 2 boundaries, one well off to our east, well off the coast, and then a cold front draped to our north, but we're kind of right in the middle of those. As I mentioned, really the only thing we're watching right now, just some high upper level cirrus clouds moving over. And then if you look very closely, you can see this dark area kind of approaching from the west to the east, and that's an area of fog, but that's expected to stay inland, and even if it did get here, really not going to be a concern for our launch window. So as we look, there's a live look at the pad right now, weather looking great, less than a 10% probability of violation, so that's greater than a 90% chance of go. Ground winds 10 to 15 knots from the west-northwest, temperature at 65 degrees, feeling nice out here in Florida. So the stage is set, the weather looking great to light up the night sky here at Cape Canaveral. Andrea?
Thanks, Brian. ULA is launching STP-3 for the Space Force's Space Systems Command. Let's learn more from Captain Ryan Burnt, SSE's Mission Integration Manager.
Thanks, Andrea. Space Test Program Number 3, or STP-3, is comprised of 2 spacecraft, both built by Northrop Grumman. Together, the spacecraft are designed to mature technology and reduce future space program risk by advancing warfighting capabilities in the areas of nuclear detonation detection, space domain awareness, weather, and communication. The first spacecraft to deploy after our long coast to GEO, STP-SAT-6, hosts the National Nuclear Security Administration's Space and Atmospheric Burst Reporting System Number 3, and NASA's Laser Communication Relay Demonstration Experiment, or LCRD. LCRD will test laser communications, which could enable the ability to send and receive data over infrared lasers at 1.2 gigabits per second from geosynchronous orbit to Earth. The second spacecraft to deploy is the Long Duration Propulsion ESPA Number 1, or LDPE-1, carrying several small experimental science and technology payloads. STP-3 is a vital national security mission, made possible only through strong government and industry partnerships. I'm honored to have played a role in bringing it to launch, and look forward to the important work we will accomplish on orbit.
ULA's Atlas V 551 rocket, the largest in the Atlas V fleet, is launching STP-3. This is the 90th Atlas V launch and ULA's 147th launch. Built in ULA's 1.6 million square foot production facility in Decatur, Alabama, the Atlas V Common Core booster is powered by an NPO Energomash RD-180 engine. The Centaur second stage is powered by an Aerojet Rocketdyne RL-10 engine, and 5 Northrop Grumman solid rocket boosters provide additional thrust at liftoff. The 2 spacecraft are encapsulated in a 5-meter diameter RUAG payload fairing. These rocket components travel from Alabama to Cape Canaveral on ULA's rocket ship. Once in Florida, a series of events lead to today's countdown. Preparations began by lifting the 107-foot booster onto the MLP in the Vertical Integration Facility at Space Launch Complex 41. Then the SRBs are mated to the booster. Next, the Centaur was lifted into position, and finally the payload fairing with the spacecraft already encapsulated was mated to the Atlas V rocket. Once the rocket is assembled, or as we like to say stacked, we begin the countdown procedure by moving it from the VIF to the pad. 6 components are used for the 20-minute, third-of-a-mile trip to the pad. The MLP weighs approximately 2 million pounds, supports the rocket, and contains air conditioning, electrical, and commodities lines. Undercarriages bear the weight of the MLP and the rocket. 2 rail cars lead the move. The payload van provides the spacecraft communication, and the ground van provides the support for the rocket. At the rear of the convoy is an environmental control system providing air conditioning to the payload and the rocket. Trackmobiles power the nearly 3 million pound convoy. The Atlas V rocket stands 196 feet, or about 60 meters, and weighs just under 1.3 million pounds, or more than 587,000 kilograms fully fueled. With the rocket on the pad, the launch team then transitions to fueling and other final preparations. ULA's Atlas V 551 rocket has several unique features that enable it to take both STP-3 spacecraft directly to geosynchronous orbit. Let's learn more about today's flight.
Centaurs off, following a guidance-commanded shutdown. This capability ensures a very precise injection. Lifespan of both spacecraft is further increased by a Centaur-provided for the Space Force. Following an approximately 40-minute coast, Centaur releases the Space Force's LDPE-1, completing the longest mission in Atlas's more than 60-year history.
This is Atlas Mission Control. The hold will be extended for at least a few minutes to wait for additional upper-level wind data. A new launch time has not yet been determined. Today's flight is dedicated to ULA employees Alex Hansen and Dean Thompson. Alex Hansen's 25-year career as a ground electrical engineer included 12 years with the Titan rocket program and 13 years supporting the Atlas V program, including activation of Space Launch Complex 41 for the first Atlas V flight in 2002. Alex was a power systems expert who worked to develop, install, and test multiple power supplies, which are a critical part of the pad ground system. Alex was also instrumental in the development of the ground systems used to roll the Atlas V to the launch pad. With such significant contributions, Alex Hansen's legacy is evident with every roll to pad and launch from Slick 41. Dean Thompson's more than 30-year career began at Boeing's Commercial Airplane Division in Wichita, Kansas. He joined Boeing's International Space Station Division in Huntsville, Alabama, followed by a move to ULA's Decatur, Alabama production facility, where he was an electrical engineer serving as the Certified Responsible Engineer Delegate for Delta IV and Atlas V avionics. Dean had delegations for the boosters, upper stages, and payload accommodations, which made him a key part of the Decatur team. As a hands-on engineer, Dean was well respected by his colleagues and missed by all of those that worked with him. This is Atlas Mission Control. A new launch time has been coordinated for 5:03 a.m. Eastern. Atlas rockets have launched many of the world's vital space assets. Let's take a look at the impressive legacy of the Atlas family of rockets.
And the RD-180 engine roars to life. And liftoff of the maiden flight of the Atlas V rocket with a Hotbird 6 spacecraft on board.
As the inaugural flight of the Atlas V lifted off on August 21, 2002, it carried with it the dreams and aspirations of thousands of rocket pioneers who had laid the foundation that made it possible. Atlas V continues the Atlas legacy of innovation and accomplishment that has been vital to our nation for more than half a century. Named after the mighty giant of Greek mythology who carried the world on his shoulders, Atlas was conceived as a weapon and a deterrent, but evolved into a system that pushed the envelope with trailblazing innovation and steadfast reliability. At the request of the Air Force, Charlie Bossert and his San Diego-based engineering team began work on a demanding set of requirements to design an intercontinental ballistic missile capable of delivering a 1,500-pound warhead to a target 5,500 miles away. Their answer, which became known as Atlas, was the top national priority in 1955 as the race with the Soviets engulfed the country. On June 11, 1957, the first Atlas flight lifted off from Space Launch Complex 14 at Cape Canaveral, Florida. The flight ended 38 seconds later, but Bossert's team had taken the first step and proven the structural integrity of their innovative pressure-stabilized steel tank. Complete success for the Air Force and Bossert's team would come just 5 months later, on December 17, 1957.
Go, honey, keep going, baby.
Though the Soviets had beaten the U.S. to space with the launch of Sputnik in October 1957, President Eisenhower would counter a year later when Atlas 10B delivered his holiday message of peace from orbit 180 miles above Earth. Known as Project SCORE, the orbiting Atlas booster became the world's first communication satellite.
This is the President of the United States speaking. Through the marvels of scientific advance, my voice is coming to you from a satellite circling in outer space.
Attention all personnel, report to the blockhouse immediately. Countdown will begin.
On September 9, 1959, Atlas 12D became America's first operational ICBM, following launch from California's Vandenberg Air Force Base. In all, 350 Atlas ICBMs were built and stood on operational alert through 1965. The surplus boosters were refurbished and used by the Air Force, the Army, the Navy, and NASA. The last refurbished booster was launched in 1995. By the early 1960s, the Atlas booster had made the transition from missile to space launch vehicle, and 1962 proved to be a pivotal year. Riding atop an Atlas booster in Project Mercury's Friendship 7 capsule, John Glenn became the first American to orbit the Earth on February 20th, 1962. Three additional Mercury flights, carrying astronauts Scott Carpenter, Wally Schirra, and Gordon Cooper, set the stage for the Gemini flights and the Apollo missions to the moon. Later that year, Atlas scored another first when Atlas 179D, equipped with an Agena upper stage, lifted off from Space Launch Complex 12 at Cape Canaveral. Its payload, NASA's Mariner 2, became the first successful interplanetary spacecraft. 1962 also marked the debut of the Centaur upper stage, the first to harness the power of liquid hydrogen. The Centaur upper stage, to this day, remains a hallmark of the Atlas system. Together, with its Agena and Centaur upper stages, the Atlas booster went on to play a significant role in America's exploration of the solar system, launching virtually every exploration mission in the 1960s and 1970s.
It was the first spacecraft that was launched from Earth that had enough energy to escape the entire solar system.
During the late 1970s and 1980s, Atlas continued to play important roles in the development of our nation's space program. In addition to building our national security presence in space, converted Atlas boosters also launched the Air Force's Navstar demonstration satellites, leading to the navigation system known today as GPS. In the late 1980s, General Dynamics saw an opportunity to bring commercial payloads back to expendable launch vehicles, and on July 25, 1990, AC-69, the first Atlas I, ushered in a new commercial era for Atlas. The commercial era brought 8 new Atlas configurations over a 14-year span, each carrying an operational payload. The commercial program has enabled breakthroughs in communications, meteorology, broadcast technology, navigation, and national security. In 1995, development of the Atlas III vehicle began. In a bold move, the Atlas booster engine system was replaced with the powerful RD-180, which generates 860,000 pounds of thrust and has throttle capability resulting in a smoother and more efficient ride. Making its debut from Space Launch Complex 36 on May 24, 2000, the Atlas III provided a substantial performance improvement over the Atlas IIAS. Reliability was increased by reducing the number of engines from 8 to 2 and the elimination of 5 staging events, as well as more than 10,000 parts.
This is Atlas Mission Control on T-minus.
In 1998, the Atlas team embarked on a development project for the United States Air Force that would forever change the Atlas vehicle.
And the RD-180 engine roars to life and liftoff of the maiden flight of the Lockheed Martin Atlas V rocket with a Hotbird 6 spacecraft on board for Eutelsat in Paris, France.
For more than 40 years, Atlas vehicles had relied on the pressure-stabilized steel tank developed by Charlie Bossert and his team. In a departure from conventional thinking, the Atlas V development replaced the tank with a structurally stable common core booster. In addition to vehicle modifications, the team took a new approach to processing and launch. Atlas V processing is done vertically, and the mobile service tower has been replaced by a mobile launch platform, which carries the entire assembled vehicle to the launch pad, ready to fuel and launch. The Atlas V is expanded to multiple payload fairing and solid rocket booster configurations, as well as re-establishing a launch capability from the West Coast at Vandenberg Air Force Base. The Atlas vehicle has a long legacy of accomplishment. This record of success, which is nearly unparalleled in the launch industry, is built on the lessons handed down from more than 60 years of Atlas experience. It is also a credit to the dedication and persistence of the Atlas team and their passion for mission success, one launch at a time.
This is Atlas Mission Control. The countdown is holding at T-minus 4 minutes while the launch team awaits acceptable high-altitude wind data for the Atlas V rocket to launch. The range has coordinated and approved a tentative new launch of 5:03 a.m. Eastern, if the next weather balloon finds favorable conditions. we've created a short tour of our launch locations here in Cape Canaveral, Florida. Let's take a look around.
With missions launched to every planet in the solar system, as well as critical national security, science, weather, and communication satellites, ULA has established a long-standing reputation for reliability and orbit accuracy in the space launch industry. At our launch site in Cape Canaveral, Florida, the story begins with ULA's Atlas and Delta rockets arriving on the RS rocket ship. The rocket ship is a specially designed cargo ship used to transport rockets from ULA's 1.6 million square foot production facility in Decatur, Alabama. Rocket ship is large enough to carry a complete Delta IV Heavy rocket. That's 3 boosters, a second stage, and a payload fairing. Once loaded, rocket ship departs ULA's dock and travels through the Tennessee River, then onto the Ohio and Mississippi rivers, then goes out into the Gulf of Mexico. From there, the ship travels through the Atlantic Ocean, around the southern tip of Florida, and north to Port Canaveral. Rocket ship was designed with several features to ensure successful delivery, including the ability to adjust its draft for shallow water and rudderless steering, which minimizes the need to tug. Atlas V boosters are transported from the ship to the high bay in the Atlas Spaceflight Operations Center, or ASOC, for final preparations. Delta IV boosters are moved to the Horizontal Integration Facility, or HIF, where they are mated together to form the Delta IV Heavy configuration. With final checks completed, the boosters are transported to the launch pad for Launch Vehicle on Stand, or LVOS. The 107-foot-long Atlas V boosters are brought to Space Launch Complex 41 and are hoisted into a vertical position using a crane and placed onto the Mobile Launch Platform, or MLP, in the Vertical Integration Facility, or VIF. Delta IV Heavy rockets are raised vertically by a fixed pad erector at Space Launch Complex 37. The fixed pad erector uses a single hydraulic piston to rotate the boosters 90 degrees inside the Mobile Service Tower, or MST. LVOS is followed by the addition of solid rocket boosters, and then the second stage. Next comes Wet Dress Rehearsal, or WDR, which is an end-to-end launch simulation, from fueling through spacecraft separation. Meanwhile, the ULA team is also working simultaneously to help the customer encapsulate their payload into the rocket's payload fairing. The encapsulated payload fairing is the final piece to be mated to the rocket. With the rocket stack complete, the spacecraft team tests all of the interfaces with the rocket and the launch pad. Once the rockets are completely assembled, final launch preps begin. For Atlas V rockets, launch countdown begins with moving the rocket from the VIF to the pad. The quarter-mile trip uses 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the MLP supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and rocket. Finally, track mobiles provide the power to move the 3.5 million pound convoy. For Delta IV Heavy rockets, the process looks quite different. Approximately 9 hours before T0, final preparations begin as 40 hydraulic cylinders at pressures nearing 3,500 psi move the 10 million pound MST. It's first raised 8 inches and then rolled back. Delta uses a carriage transporter system, traveling at about a quarter mile per hour. It takes about 25 minutes to roll the MST to its launch position, 345 feet north of the Delta IV rocket. The Delta IV rocket stands 217 feet tall, or about 21 stories, and weighs more than 900,000 pounds fully fueled. On the day of launch, nearly 30 engineers and managers are polled for system status and readiness to proceed.
Status check to proceed with terminal count, Atlas Systems, propulsion.
This is the final status check before launch for all Atlas and Delta vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants.
Range coordinator. Clear to proceed. Launch director.
Launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count.
If the rocket is ready for flight and the weather is within the launch commit criteria, then polling will be completed and the team will have given the go for launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's ignition. And liftoff of the United Launch Alliance Atlas V rocket.
For a typical Atlas V flight, the main engine and solid rocket boosters ignite to lift the rocket off the pad. Shortly after liftoff, the rocket begins a pitchover to attain the proper flight path, minimizing the dynamic pressure the vehicle experiences during flight. Within the first few minutes of flight, the vehicle reaches Mach 1, the speed of sound, followed by jettison of the solid rocket boosters. About 4 minutes later, propellant levels deplete and the booster engine shuts down, followed by release of the booster stage. At various times in flight, depending on the mission, the vehicle jettisons its payload fairing. From there, the second stage will continue carrying the spacecraft towards its destination with planned engine starts and stops. Finally, Centaur will release the spacecraft in its target orbit to continue its journey.
This is Atlas Mission Control. The countdown is still holding at T-minus 4 minutes while the launch team awaits acceptable high-altitude wind data. A series of balloons have been sent aloft over the course of the countdown to measure the speed and direction of upper-level winds that the Atlas V will experience during flight. That data is then assessed to verify conditions are within the structural and controllability limits of the launch vehicle configuration.
SC9, go.
SC, you're on your network.
In October, ULA's Atlas V rocket launched NASA's Lucy on its long journey to Jupiter's Trojan asteroids. Let's take another look at that historic flight.
We are so excited to have been selected to fly this Lucy mission. It is humbling to be entrusted with something like this that is going to shed new light on the origins of our solar system by visiting primordial material gathered by the Lagrange points of Jupiter as it formed the early solar system. This is so exciting for us. Our team has worked so hard. We are honored to work with the brilliant people at NASA who put this together.
We're starting a 12-year journey of this amazing spacecraft, really 8 missions in one. For me, as we are launching this, I think of the amazing team that brought it together. On the rocket it says Lucy Strong, and for me that's the battle cry that brought the team together. Congratulations to everybody.
Go Atlas.
Go Centaur.
Go Lucy.
3, 2, 1, 0. Liftoff. Atlas V takes flight, sending Lucy to uncover the fossils of our solar system.
Tower clear.
Has begun the pitch yaw. We have indication of successful separation of the Lucy spacecraft.
L minus 40 minutes.
This is Atlas Mission Control. The countdown is still holding at T-minus 4 minutes while the launch team awaits high-altitude wind data. Today's available launch window, which is determined by orbital requirements of the STP-3 payloads, remains open through 6:04 a.m. Eastern Time for the Atlas V rocket to launch from Cape Canaveral Space Force Station in Florida. At the present time, the launch team is postured to resume the countdown for a launch in the middle of the window at 5:03 a.m. Eastern. The ULA team continues to make progress on development of our Vulcan Centaur rocket. Here is an update.
Vulcan Centaur production begins with aluminum sheets, expertly machined to remove more than 2/3 of the weight, resulting in the structurally strong yet lightweight orthogrid panels that form Vulcan's propellant tanks. The panels are then bump pressed to form the curves required to complete the tanks. At the same time, rings, adapters, and other structural components are precision milled. Next, the aluminum domes, panels, and other structures that form Vulcan's propellant tanks are first cleaned and etched to a smooth, even surface, and then anodized to harden and prevent corrosion. Following an ultrasonic inspection, 5 completed panels for the liquefied natural gas, or LNG tank, are assembled and joined together using friction stir welding. Unlike traditional welding, where filler material is used to join components, friction stir welding uses a head to stir the metal of the 2 panels together as it moves down the seam. The resulting joint is stronger and produces a lighter weight, higher performing tank. The process is repeated to create the liquid oxygen, or LOX tank, followed by attaching domes to complete the tanks. Circumferential friction stir welding is then used to join the 2 propellant tanks that comprise the Vulcan booster. As production continues on the booster stage, stretch-forming gore panels for the Centaur's second stage propellant tanks is underway. The stainless steel gore panels are welded together to create the propellant tank domes. The gore welder is one of several highly specialized welding stations in the Centaur production process. Just down the aisle, Centaur 5's massive intermediate bulkhead is mated to its ultra-thin tank. Once both propellant tanks are welded, they're mated together to create the Centaur 5 second stage. Once the propellant tanks are joined, the 5.4-meter booster is sprayed with foam insulation before moving to final assembly. Twin BE-4 engines are hot-fired and then mated to Vulcan's thrust structure. With production complete, the booster makes its way onto ULA's rocket ship for its journey to the launch site. Meanwhile, at Cape Canaveral's Space Launch Complex 41, the water suppression system has been upgraded and tested, along with other modifications, including new, larger fuel storage tanks. In the Vertical Integration Facility, or VIF, platforms have been modified to accommodate the larger Vulcan rocket. Following the 8-day journey to Cape Canaveral, the booster is offloaded and transported to the VIF, where it is lifted onto the newly constructed Vulcan Launch Platform, or VLP. The first Vulcan booster then travels a third of a mile to the pad for testing, followed by 2.7 miles to the Spaceflight Processing Operations Center, or SPOC, for additional testing. This launch site testing culminates with another trip to the pad, where the LOX and LNG tanks will be filled and chilled to flight levels and temperatures.
LCLD, gentlemen.
Go, LD.
Roger, please load our contingency address file.
Roger. And do you have the file number?
Roger, sir. File number is 06.
Roger that. Flight Control LC, that one. Go ahead, this Flight Control. Per operation 60, step 220. Load contingency file adjust AV093_06.
Roger.
L minus 25 minutes.
This is Atlas Mission Control. The countdown is still holding at T-minus 4 minutes while the launch team awaits high-altitude wind data. We are proceeding towards the new launch time of 5:03 a.m. Eastern. On board the Atlas V rocket, there are several payloads including NASA technology that could revolutionize how we communicate to and from space. Here's more on NASA's Laser Communications Relay Demonstration, or LCRD.
Since 1958, NASA has relied on radio wave technology to talk with missions in space. Today, we're developing a better way to get spacecraft data back to Earth. That's where the Laser Communications Relay Demonstration, or LCRD, comes in. Built and managed by NASA's Goddard Space Flight Center, LCRD will send and receive near-infrared laser beams to and from Earth. As NASA's first long-duration test of optical communications technology, the mission aims to perfect space and ground-based technologies. So why lasers? Laser communications can transmit up to 100 times more data per second than previous systems by using a shorter wavelength of energy. With this increased bandwidth, missions can send larger files and even live high-definition video from space. Laser communication systems are smaller and more efficient than radio wave technology. They leave more room for science instruments, are cheaper to launch, and require less energy on board the spacecraft. These benefits extend to receivers on the ground. Earth-based laser communication receivers can be up to 44 times smaller than the current radio antennas. LCRD is the next step in making these technologies a reality, helping NASA to push the boundaries of scientific discovery and exploration. Eventually, NASA will integrate this technology into future missions, as well as share it with commercial companies.
LD, LC, net 1.
LD on 1.
Okay, you are tracking for our new T0 of 1003 Zulu, and L20, I'm expecting SV to go internal, and we'll reevaluate winds prior to go to IFPS power.
Roger, concur.
L minus 21 minutes.
LCLD, Channel 1.
Go.
Roger, sir. We've got a report that upper level winds will be red at the open of our window. Stand by for coordination of a new T0.
Roger.
Spacecraft coordinator LC, that one.
SCN1. SCN1, go.
Yeah, so we'll stand by until I get further direction on T0 for spacecraft coordination.
Understood.
LCLD, Channel 1.
Go, LD.
Roger, sir. Please coordinate a new T0 with the range of 10:19Z. That's 10:19Z.
Roger. RC, LC, net 1.
RCN1.
Please coordinate a new T0 of 10:19 Zulu.
Roger and work.
ALC, please set the clock of 10:190.
Roger.
And spacecraft coordinator LC.
Is SC on 1?
Yeah, if I need to understand the SV configuration.
Roger, stand by.
Roger.
LCALC.
Go.
Countdown clock has been set with new T0.
Roger.
LC, SC on 1.
Go.
Both spacecraft are external and standing by for the new T0 of 1019.
Roger.
L minus 30 minutes.
This is Atlas Mission Control. The launch director, James Whalen, has instructed the team to coordinate a new launch time of 5:19 a.m. Eastern. Space communications infrastructure in space and on the ground enables the data collected by missions to reach Earth, upgrading our capacity for discovery. Since the dawn of space exploration, NASA missions have relied on radio frequencies for this transfer of information. NASA's Laser Communications Relay Demonstration will launch to space, showcasing the vast benefits of laser communications. LCRD's ground stations, known as Optical Ground Station 1 and 2, are critical to the mission's success.
L minus 25 minutes. L minus 23 minutes.
Flight control, verify IFPS power is disabled.
Verified.
minus 21 minutes.
This is Atlas Mission Control. The countdown remains holding at T-minus 4 minutes while the team continues to wait on the winds aloft. A new T0 is planned at 5:19 a.m. Eastern. Today's trajectory is long and complex. Here's ULA's President and CEO, Tori Bruno, to explain the flight in more detail.
I want to talk to you about our next mission, STP-3. It's a very, very cool mission. I'm here in the DOSC, the Operations Center in Denver, which is going to be filled with engineers in just a few days. This mission is a rare and unique trajectory, something we call a direct injection into GSO, or geosynchronous orbit. We're going to use our biggest Atlas, the 551, the Bruiser, 5 solid rocket motors, 2.6 million pounds of thrust at liftoff to do this. The spacecraft is also pretty cool, but that's classified. So back to the rocket. When we lift off, we're going to go straight up into the sky. We're going to be nearly orbital when the first stage finishes. It'll just take a few minutes to consume all that propellant, and then Centaur will take over. It'll take us with a very short burn just into a LEO parking orbit, so we can coast around to be perfectly aligned for the latitude we want for this spacecraft. Then it's going to do a hard burn. It's going to throw us out on a big elliptical orbit, a home and transfer that exactly intersects at its highest altitude with the destination. Normally, you'd be done right now, and the rocket would drop you off, and the spacecraft would have to use its own fuel to circularize that orbit, shortening its life. But not this time. This time, Centaur's going to go all the way. We're going to coast for 5 long hours, because that's how long it takes to get from LEO to GEO. And then just as we are intersecting that altitude, Centaur will come back to life, fire up for another burn, and lift that perigee all the way out into a perfect circular orbit at geosynchronous altitude 36,000 kilometers above Earth, a period that is exactly a day, so the spacecraft appears to hover in the sky. Go Atlas, go Centaur, go STP-3.
LCLD, Channel 1.
Go ahead.
Roger, sir. We are continuing to proceed. We'll have the final winds update shortly, but we are green at this moment and continuing to proceed.
Roger.
L minus 15 minutes.
LC, this is SAT-6 on channel 1.
Go.
STP SAT-6 is on internal power and is prepared to enable the in-flight power system.
Roger. Flight control, enable SAT-6 IFPS.
Roger. SAT-6 IFPS enabled.
Roger. SAT-6 MM, LC Net 1.
SAT-6.
Begin telemetry verifications.
Verifying.
As you heard moments ago, we are currently green for weather. We are proceeding towards a 5:19 a.m. Eastern launch. Polling will begin in just a few moments.
L minus 13 minutes.
LC, this is LVPE on channel 1.
Go.
LVPE1 is on internal power and is prepared to enable the in-flight power system.
Roger. Flight control, enable LDPE IFPS.
Roger. LDPE IFPS enabled.
Roger. LDPE MM, LC Net 1.
This is LDPE.
Begin telemetry verifications.
Roger.
Flight control, LC.
Go ahead, this flight control.
Form option 409, RP1 temp update.
Roger. LC, this flight control 409 is complete.
Roger.
L minus 10 minutes. All communications switch to channel 1. All personnel and visitors remain in present position until launch. Maintain operational silence in the LCC.
Terminal count briefing. If a condition exceeds a launch constraint anytime after the terminal count status check, the observer shall announce hold, hold, hold on channel 1, identify their station, and briefly state the reason for the hold. Flight control, perform launch on time verification.
Roger.
OSM, place
SDA1 is go.
You're on net 1. OSM, place SRB ignition SNA switch in the enable position.
SRB ignition enabled.
LOX 2, verify CISA purge flowing GN2 to the CISA.
Verified.
OSM, verify the FCO, ROC, and OSM hold fire switches are in the proceed position.
Ready to proceed.
RLM, verify the red line monitor and event table in the correct configuration for terminal count.
Verified.
L minus 9 minutes.
RC, verify solar radiation acceptable for launch.
Verified. Launch on time verified.
Roger. LC switch to the ready position. All steps are complete prior to the status check.
L minus 8 minutes.
We remain in the planned 30-minute hold as we continue towards liftoff. In a few moments, launch conductor Scott Barney will pull the launch team for the final go to pick up the countdown. 29 engineers and managers are pulled for their system status and readiness to proceed. This is the final status check for all Atlas vehicle systems, ground systems, spacecraft, and the U.S. Space Force Eastern Range. The vehicle system readiness pull includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling.
L minus 7 minutes.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
HASGAS.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RF FTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operations support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
You have permission to launch.
Proceeding with the count. ALC, verify T0 is set for 10:190.
Verified.
Polling is complete, and the ULA launch team and the Space Force mission director go for launch. From T-minus 4 minutes until launch, you will be listening to Scott Barney and his team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes leading to launch, including verifying fuel tank levels and pressures in the booster and Centaur, as well as arming the flight termination system. At T-minus 25 seconds, you'll hear Go Atlas, Go Centaur, Go STP-3. This is the final status check of Atlas, Centaur, and STP-3 readiness. At T-minus 3 seconds, the main engine ignites, followed by ignition of the solid rocket boosters. Then after seeing the Atlas V lift off the launch pad, you'll begin hearing flight commentator Jesse Gonzalez providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
On my mark, the time will be T-minus 4 minutes and counting. 3, 2, 1, mark. .355.
Ground
The
pyro
countdown
enabled.
clock is resumed and we are go for launch at 5:19 a.m. Eastern. With liftoff approaching, we are going to turn up the volume on our launch team so you can hear the final preparations taking place.
Three minutes.
Atlas tanks to flight pressure.
Securing LO2 topping.
250.
FCS internal.
LDPE-1 is configured for launch.
Roger.
One minute 59.
Vehicle internal.
155.
Launch sequencer start.
150.
Securing Centaur LH2. Securing Centaur LO2.
.140.
Launch enabled.
137.
FCS armed.
T-minus 90 seconds. The launch vehicle, payload ground systems, and Eastern Range are go for launch.
120.
OCUs armed.
SCS count started.
115.
Reduce CCS for launch.
Roger.
110.
Vent valves locked.
T-minus 1 minute.
Rock. Report range status.
Range green.
.40 seconds.
Stable at step 3.
.28.
ECS reduced for launch.
Roger.
25.
Status check.
Go Atlas.
Go Centaur. Go STP-3.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
Vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed loop control. SRB chamber pressures continue to look nominal. RD-180 pump speed and fuel injector pressures continue to look good. Mach 1, Atlas V is now supersonic. Passing 45 seconds into flight, vehicle is now passing through max Q, maximum dynamic pressure. And the RD-180 is throttling back up as expected. Engine response looks good. Passing 1 minute into flight, the vehicle is now 9 miles in altitude, 7 miles downrange, traveling at 2,200 miles per hour. And the RD-180 is throttling down again as expected. Engine response looks good. Standing by for SRB burnout shortly. And just past a minute and a half into flight, we have burnout on all 5 SRBs. Burnout pressure signatures are looking good, and the RD-180 is being throttled back up as expected following SRB burnout, standing by for jettison shortly. And we have good indication of jettison of all 5 SRBs, and the vehicle has gone to closed loop Q alpha limited steering following SRB jettison. Body rates are looking good. And coming up on 2.5 minutes into flight, a little over 2 minutes remaining in the boost phase of flight. And the RD-180 is now throttling to maintain a constant 2.5 G acceleration limit. Engine response and vehicle response looks good. And the Centaur reaction control system is now pressurizing to flight levels. Passing 3 minutes into flight, the RD-180 pump speeds and fuel injector pressures continue to look good. The vehicle body rates look very good for this phase in flight. And the vehicle is now 65 miles in altitude, 150 miles downrange, traveling at 7,800 miles per hour. Standing by for payload fairing jettison shortly. And we have good indication of payload fairing jettison. And we have Centaur forward load reactor deck jettison. And the RD-180 is throttling back up as expected. Engine response looks good. And the RD-180 is now throttling to maintain a constant 5G acceleration limit. Engine response continues to look good. And Centaur has begun the boost phase chill down portion of flight to thermally condition the RL-10 for operation. And we've had BECO, booster engine cutoff. And we've had successful stage separation. And saying pre-start on the RL-10. And we've had ignition for the first burn. This will be the first of 3 Centaur burns for today's mission and will last a little under 6 minutes. The RL-10 startup parameters are looking good, and seeing the body rates close out nicely.
This is Atlas Mission Control at T plus 5 minutes and 21 seconds. You just heard our flight commentator, Jesse Gonzalez, confirm the successful completion of the early phase of today's flight, and all systems continue to operate nominally. Our next event, Centaur main engine cutoff, will occur in approximately 5 minutes. I'm now joined by Emma Coates. She's RUOG's Payload Fairing Program Manager. Thank you so much for being here with us today.
Yes, thanks so much for having me. It's such an accomplishment to be here and to witness the jettison of our first payload fairing, our first out-of-autoclave payload fairing.
Yes, it's been great. I mean, it's a huge accomplishment for the team, and we're going to talk a lot about what that means out-of-autoclave manufacturing. But as you know, you guys have been producing payload fairings for us for quite some time, but this is the first one that we've flown using the out-of-autoclave process. Can you explain to us a little bit about what that means?
Yeah, so normally when we talk in autoclave or out of autoclave, we're talking about the curing or the baking process that goes into creating a payload fairing or a composite structure. The autoclave itself is actually the container that is performing this curing or baking process.
Great. So in autoclave versus out of autoclave, what are some of the benefits of the out of autoclave process?
So a few of the benefits of the out of autoclave process is actually the fact that we're able to be a little bit lighter in weight. We like that. Right. So we're saving time and cost and everything also because we don't have to have that same internal pressure requirement that's used in the in autoclave process. We're able to lay up an entire half shell of a fairing with just one oven cure cycle, which saves a ton of time.
That's great. I mean, a lot of efficiencies there. We're all about efficiencies and making things better going forward. So what a huge accomplishment and what a fantastic process you just kind of went through for us. So as you know, you have a production facility that also shares our ULA Decatur production facility. This was the first fairing that was actually produced there and flown now. Can you tell us a little bit about the partnership between RUOG and ULA?
Gotcha. Yeah, so we have many years that, as you mentioned before, we've got a ton of years of partnership with ULA, both on our U.S. Switzerland, on our RUOG Switzerland side and our RUOG U.S. side. But with this being the first one out of Decatur, this actually allowed us to be super close to you guys, sharing that wall essentially. So we were actually able to issue, I guess, better delivery, I guess would be the time frame or be the thing, but we were able to have better delivery times, save on logistics, which is again saving on a ton of costs.
We love the efficiency. Again, we're talking about efficiencies here.
Yeah.
I mean, the one thing that's been great, we obviously talked about process efficiencies, which was awesome, but I mean, you're talking about process flow efficiencies as well. We literally share a wall with our two facilities, so you can't get more efficient than that.
Yeah.
All right, so something near and dear to my heart. I've been lucky enough to work with you on the Vulcan development program for a long time now. As our viewers may not know, you're actually producing the Vulcan payload fairing for us as well. So can you give us a little bit of a status on where we're at with that development program?
Sure. So we're actually nearing the completion of our qualification process for that. And of course, we're gathering all of our lessons learned from this launch and any of the other payload fairings we're building as well. That way we can make sure that Vulcan is also a success as well.
Right, and it's been so great to watch that qualification testing that we've been doing at Marshall Space Flight Center. So excited to see that come to completion and fruition and things like that. So it's been really great, you know, learning more about the first out of autoclave fairing. I'm so happy to have you here. Emma, thank you for joining us, and I hope you have a good rest of your day. And again, congratulations.
Thanks so much for having me.
All right. Okay, let's get back to the mission. We're coming up on the end of the first of 3 Centaur engine burns. Our next event is the first Centaur main engine cutoff for MECO 1. Once again, here's Jesse Gonzalez.
And standing by for MECO 1 shortly. And seeing PU go to open loop control in preparation for MECO. And we have MECO. Engine cutoff pressure signatures look good. Centaur will coast for approximately 1 hour prior to the next burn. And the RCS system is now commanding 100% settling to settle propellants in the tank following the burn.
This is Atlas Mission Control at T plus 11 minutes and 30 seconds. Jesse Gonzalez just reported the successful completion of the first of 3 Centaur engine burns. Centaur is now in coasting over the Atlantic Ocean west of Africa, but we still have a long way to go. STPSat-6 is scheduled to separate from Centaur into geosynchronous orbit in just about 6 hours and 20 minutes, followed by 40 minutes later by separation of LDPE-1. To tell us more about the spacecraft, I am now joined by the STPSat-6 Program Director, Ray Crow. Ray, thank you so much for being here today.
Oh, I'm absolutely delighted to be here today. It is a great day for our nation.
It is a great day for our nation.
Absolutely fantastic.
Very exciting. Finally got off the ground,
Yeah.
which was great. But thank you for taking a couple of minutes off console to be here with us today.
My pleasure.
I'm excited to learn more about STPSat-6. So to get us started into the questions, why don't you tell us a little bit more about Northrop Grumman's role in this mission?
I'll describe Northrop Grumman's role in this mission, but I'll give you a bonus item.
Oh, great.
I just got a note from our engineers here on site, and we are receiving spacecraft telemetry as expected. Absolutely
Oh, that's
fantastic.
amazing. I love the up-to-date information.
So we have a very significant role in this mission. I'll start with the Northrop Grumman contribution from the top of the rocket to the bottom of
Great.
the rocket. There are 2 spacecraft. The top spacecraft is STPSat-6. STPSat-6's mission is to explore science that will inform a generation of spacecraft design and mission design. Northrop Grumman's role for STPSat-6: design, development, test, integration of the payloads, and support of the mission over a 10-year period of time.
That's quite a life cycle.
It's a fantastic life cycle, but you contrast that to this program has been under motion for the last 7 years. So this moment.
Long day coming.
Punctuation point between 7 years of development and the first hours of 10 years of operation. So we are very excited about that. As we move down the stack, LDPE number 1. LDPE stands for Long Duration Propulsive EELV.
Very good.
An acronym
Yes.
within an acronym.
Love those.
So think about LDPE number 1. It is a ring. However, it is an extremely smart ring. It is a spacecraft, and you can affix payloads to that spacecraft. There are so many advanced scientific payloads that are sitting on shelves right now, and for lack of financial resources, we cannot get those in space. Enter LDPE number 1 and the platform ESPISTAR produced by Northrop Grumman. So we have an inexpensive and an easy way to integrate payloads that represent the forefront of technology, a way to reduce risk, to test payloads in space early, and even better than that, the opportunity for residual operational capability. We continue our walk down the vehicle this morning, and we have had, it is a pride point for us, and the pride point is the relationship with Atlas over a 3-decade, more than 30-year period of time.
A long heritage there.
Extremely long heritage. So everyone, of course, saw those magnificent GEM engines. Those are produced by Northrop Grumman.
Yes.
We also produce some composite structures for the Atlas as well. So a great deal of Northrop Grumman content, and certainly a great deal of employee pride when we see an event like this and prepare for 10 years of operation.
It's quite an integrated team effort, but it's really amazing to see all of the aspects that Northrop Grumman has been involved in over this long period of time. So again, congratulations on us finally getting here today. So let's take a look now at our payload. What makes STP-SAT-6 unique?
Well, we'll start with a very capable and a very prestigious client, the U.S. Space Force. We work with the Space Test Program located at Kirtland Air Force Base. Their leadership in this has been absolutely remarkable. And then as we work through the rest of the mission, and so STP-SAT-6 has set all sorts of records on our Dulles campus. One for today is this is our 200th spacecraft.
Congratulations!
From our Dulles campus.
It's exciting.
And we'll say LDPE was 201. But,
okay, that's fair. That's fair.
STP-SAT-6 is number 200.
Okay.
We have set perhaps 25 records for spacecraft that have moved through our campus. It is our first rad-hard bus. It is a redundant bus. It is designed for a 10-year life, and it has been just an absolute delight to develop and to build.
I mean, that's great. It's truly amazing to hear about all of the activities that went in today and how unique the spacecraft is. So in terms of the actual mission today, can you give us a little bit more information about the mission milestones we can expect to see?
Absolutely. So we'll start with 20 minutes before we were launched today. We went to internal power, but internal power for us means we are on our batteries, but the Centaur carries batteries as well.
Correct.
And that assures us that when we are released, that we will have, let us say, a full head of steam. Our batteries will be fully charged. So we will be attached to the Centaur for another 6.5 hours.
It's a very long mission today.
It is actually the length of this mission is a record.
Another record.
Another record.
Yeah, for both of us actually.
Absolutely.
Yeah.
So also great there too.
Mm-hmm.
So after 6.5 hours, we will pop off the vehicle. Gently pop off the vehicle.
We like a gentle ride. Delivery to the right place.
Delivery to the right place. And so on this 6.5 ascent, we are in a mode called all safe, which means we cannot accidentally deploy any of our mechanical appendages. So we will pop off the rocket. At that time, thrusters will be enabled, wheels will be enabled, our solar array will deploy, and we will find the sun. And then the ground segment will acquire us. At that point, that's when it's thumbs up and the launch has been completely successful when we are delivered on orbit. Once on orbit, we will undergo a test regime 66 days, plus or minus 66 days.
A little bit longer.
And then we will transition to government operation, and that puts us in a role where we will support these operations for a decade.
Oh, great. It's a really long time. I mean, we're talking about long times to get us to orbit. Now we're talking long time in orbit. I mean, it's truly great to hear all about the heritage, the history, and our mission today. So before we let you go, is there anything else you'd like to add?
Well, absolutely.
Always, yes.
Always, absolutely. So here's what I would add today. I will finish today with the words that we use when we start every major meeting with our stakeholders. And when I say stakeholders, and when I use the word team, team goes far beyond the boundaries of the Northrop Grumman employee family. It includes the Space Force, NNSA, NASA, ULA, and a broad community of stakeholders. And the words that we use are this: if you're willing to work as a team, anything is possible. That's my message today.
Yeah, I mean, we all know how complicated everything is with this entire process. So quite a collaborative effort. And congratulations again today. I have certainly appreciated all of the information you've provided to us. I know our viewers have enjoyed it as well. I can certainly feel your enthusiasm. So I know everybody's really appreciated that. But certainly, thank you for spending some time with me today and letting us know a little bit more about your role in the mission.
Thank you for the opportunity.
Great.
I appreciate it very much.
Thank you so much.
Have a great day.
All right. Before I toss today's live coverage back to our NASA partners, where you'll hear more about the Laser Communication Relay Demonstration, I'd like to thank Jesse Gonzalez for his participation in today's show, as well as Brian Sizik from the Space Launch Delta 45 weather. You can stay updated on today's long ascent to geosynchronous orbit with ULA's live blog at ulalaunch.com, or join the conversation on Twitter and Facebook. I'm Andrea Linhoff. Thanks for joining me bright and early today. Before we hand you back to NASA coverage, let's take one more look at the liftoff from today at 5:19 a.m. Eastern. Have a good rest of your day. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
Vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed loop control. SRB chamber pressures continue to look nominal. RD-180 pump.
If you're just joining us, welcome to NASA's live coverage of the Laser Communications Relay Demonstration, or LCRD. It launched about 20 minutes ago from Cape Canaveral Space Force Station as part of the Space Test Program 3 mission. LCRD will demonstrate the unique capabilities of laser, also known as optical communications, versus the radio systems NASA uses now. And here with me this morning is Jeff Sheehy. He's the Chief Engineer for NASA's Space Technology Mission Directorate. Jeff, wasn't that a beautiful launch?
Oh, they're always amazing. I mean, right out there, the launch, the bright flash, and then you wait a few seconds and you hear that sound that kind of beats against your chest. I've seen a number of launches now, and they never get old.
Yeah, definitely worth the wait this morning. And so talk to me about, LCRD, again, is on its way now, but there's still a lot we need to monitor, right?
Yeah, the spacecraft is going to be delivered to near its final orbital home in about 6 hours and 10 minutes from now. It'll be dropped off from the upper stage of the launch vehicle. And then it'll maneuver into place over the course of a couple of weeks. During those couple of weeks, the Space Force will be checking out their spacecraft. The spacecraft is more than just a host platform in terms of a place to mount all the LCRD stuff, but LCRD is going to rely on spacecraft systems to be working. So they'll bring up the spacecraft, check it out, make sure everything's working okay.
Yeah.
And then when we know about 2.5 weeks from now, when the spacecraft is in its proper orbit, when the spacecraft is all been checked out, we'll be able to turn on the LCRD payload.
Yeah, that's really exciting. And then when do you say, hey, this mission was a success? Is there a threshold we need to cross?
There's a number of objectives that we have for the mission. All of the technology demonstrations that we do, we write formal requirements, and we have a set of mission objectives. And this one's no different. We've got objectives that will demonstrate the capability of transmitting data at high data rates from the ground to the spacecraft, from the spacecraft to the ground. Ultimately, there'll be other assets in space on the ISS, on the Orion capsule. We'll communicate between those and relay that data to the ground. The R in LCRD, the relay part, is really an important aspect of the demonstration here. It's not just about being able to send data from a spacecraft to ground, but relay that data to between other assets in space. So when we accomplish that, we'll basically show that, hey, it works great. That's what we're trying to do. We're trying to demonstrate how well does this work anyway. And so when we demonstrate that it works well, then we'll try out different operational scenarios. What we want to do is demonstrate the capability to a point where a mission planner could say, hey, that's a technology that I can really use to benefit my mission. So we'll try out different operational scenarios. We're going to be taking a lot of data on how well does the laser penetrate through the atmosphere, how well do we receive the data at these ground stations in California and Hawaii. There'll be some atmospheric interference. We have adaptive optics in the ground station to be able to correct for that.
So with this launch, it just means more work for you guys.
Yeah, we were just talking to the program manager before we came on, and he said, yeah, this is checking one thing off, but now the real work starts.
Right, but it's exciting work, and I'm so glad you guys got to launch today, and yeah, we'll just see when the experiments start in March. So thank you, Jeff.
You're welcome.
Thank you so much. And LCRD will be NASA's first two-way end-to-end optical relay because it can both send and receive data at once. Check out this video for why that is so significant.
LCRD will relay sample data, like glimpses of planetary surfaces or satellite health down to Earth over infrared lasers. Historically, NASA has used radio waves to communicate. When we landed on the moon in 1969, Neil Armstrong's first words came across radio waves.
It's one small step for man, one giant leap for mankind.
When we go back to the moon, we're going to stay longer and explore more. With so many new and exciting things happening on the moon, missions will need a better way to talk with Earth. And that's where lasers come in. LCRD will demo the vast capability of laser communications. This includes transmitting 10 to 100 times more information to Earth than is possible using radio systems, meaning missions can send more detailed photos, videos, and data. When LCRD reaches its destination, it will spend 2 years conducting experiments that will be developed by NASA and our friends in industry and academia. LCRD's first orbiting experimental user will be the International Space Station. Astronauts live and work there, conducting research about life in space, microgravity, biology, and more. Using lasers, the station will be able to relay more experimental data to scientists on Earth. Laser systems are great for missions like the space station because they weigh less, are smaller, and use less power than radio systems. A smaller size means more room for science instruments. Less weight means a less expensive launch. Less power means less drain on the spacecraft's batteries. LCRD and the space station will work together and demonstrate laser communications near Earth. This will help prove laser systems are an option for future expeditions back to the moon and then on to Mars.
Thanks again for joining us for this live launch coverage of LCRD. Again, it will orbit about 22,000 miles above the Earth's surface while it conducts 2 years worth of experiments. You can follow all the updates at nasa.gov/lasercoms. You can see it right there on the bottom of your screen. And you can never get enough video of a beautiful launch, so let's close out the show with another replay. Have a wonderful day, everyone.
T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of the United Launch Alliance Atlas V rocket with the STP-3 mission for the United States Space Force.
Vehicle has cleared the tower and is beginning the pitch over program. And the RD-180 is throttling down slightly as expected. Engine response looks good. And passing 20 seconds into flight, the PU system has gone to closed-loop control. SRB chamber pressures continue to look nominal. RD-180 pump speed and fuel injector pressures continue to look